Hi everyone, thank you for attending. My name is Nate Desimone. I'm a firmware engineer at Intel Corporation, and today I'm going to be talking about the open source in UEFI firmware efforts we have going on at Intel, and a new initiative called Minimum Platform, which intends to make that a reality. So I'll start off with some technical background, the problem we're trying to solve, the minimum platform architecture, and the advanced feature design and how LinuxBoot can fit into that. So the building blocks for traditional EFI firmware really come down to three buckets: platform, silicon, and core. Core is the Tiano core that's already open source, driven by industry standards, and provides a generic framework for building firmware. The FSP is typically how we provide our silicon reference code. This is typically closed source. It has some tie to a specific class of hardware. For Intel, that's going to be specific SoCs and chipsets. And it's typically proprietary code, not standardized. Sometimes it is. Platform is really kind of the part that's missing. This is typically closed source. It generally only supports one specific board or a specific family of boards. Every OEM has their own implementation. And it's really the piece that is missing today that we need to create open source EFI firmware. So firmware is built on standards. On the bottom end, we have hardware which is driven by industry standards like USB, PCI-SIG, JEDEC, etc. On the top end, we have the interface to the operating system, whether it be EFI or some other boot spec. The SoC code is covered by FSP, and then platform is really the code that brings all of these pieces together and creates a cohesive firmware implementation that boots the system from reset up until the OS. So for silicon initialization, we generally use the Intel FSP as our distribution mechanism. Generally, the resources needed to implement the FSP are not publicly available, so we use the FSP as a means to provide that to the community. So FSP 2.1 is a new version of the specification that we released last year. The primary objective of this spec update was better integration with EFI firmware. There's the existing mode that most people will probably be familiar with called API mode. This is basically the way FSP has always worked since it originally started. The new feature in 2.1 is dispatch mode, which exposes the FSP as a firmware volume so that the drivers inside it can be executed by the platform provided EFI firmware directly. It greatly improves efficiency if you're using an EFI firmware design, and it really fits in quite well with Min platform. Of course, since we now have dispatch mode, we have a need for open source EFI firmware. So if you look at current firmware implementations across the ecosystem of EFI, it really is kind of a jungle. So every OEM and ODM has their own implementation. It's usually vastly different from implementations from other vendors. And it doesn't really need to be. The things that are different are things that don't really provide much value add. And the result is that EFI has a fragmentation problem, much like the Android fragmentation problem. So it's difficult to understand what's going on if you look at any specific design, because it varies so much between vendor to vendor. And that also makes it difficult to secure, because The same thing is done in different ways without need. So with minimum platform, we plan to fix this. It's a new design philosophy for EFI. We want to be minimal, consistent, approachable, and secure. So we really are taking the large monolithic platform bucket and breaking it up into 3 separate buckets now: board, features, and min platform. So min platform is a base which provides most of the common platform code implementation. And then board is been isolated just to the specific code changes needed to support certain motherboards, different GPIO configurations, different number of PCIe controllers, different PCI port layout, that kind of thing. And then features are features like the IPMI support, SM BIOS, BIOS setup, that kind of thing. So the goal is really kind of like the Android Project Treble, if anybody's familiar with that. It's intended to reduce fragmentation by providing common open implementations of similar feature sets across vendors. So less fragmentation, open collaboration. We have a divide and conquer strategy for power on and integration with Min platform, and it's implemented using what we call the boot stages. So stage 1 through stage 6 provides varying levels of feature completeness, which we found through our experience tends to match how a platform power on goes. So when you start out with stage 1, it's really not much. It's pretty much just you can support the JTAG debugger, you can see debug messages on serial port, and that's about it. Stage 2 is we've gotten through DRAM init, so MRC has run, and we have main memory. Other than that, still very minimal. Stage 3 is enough to boot to the EFI shell. So this includes a console of some kind, whether it be a serial port or a video card with a keyboard. And it also provides enough to execute EFI shell commands. Now, not necessarily enough to get to the operating system. For that, you need stage 4, which gives you the ACPI tables required to boot an OS kernel, any SMM needed for runtime features, and minimal functionality in the OS kernel. For example, at stage 4, you might not be able to load high-performance graphics drivers and might only be able to do basic frame buffer, that kind of stuff. So stage 5 is stage 4 with security. So we sign the firmware now, and we can authenticate it, and we can lock any security-sensitive registers. And finally, stage 6 is the full-featured firmware implementation. So at this stage, you really have a product quality firmware ready to be used and mass deployed. So advanced features are a la carte approach to firmware features. So many different customers will want different feature sets and different levels of complexity to their firmware. And Min platform allows this by making each feature modular and individually selectable. So for example, one might not want USB debugging support on some images, but maybe on other images. You can individually turn that on and off. You can individually turn the SM BIOS on and off. EFI networking, it's something that some people want, some people don't. Same with BIOS setup and many different implementations of updating firmware, whether it be capsule or the verified boot or many different ways, right? So to make a vertically integrated, customized firmware implementation, everyone's going to want a slightly different answer for all of these things. And Min Platform gives you the flexibility to choose what you want. And really, our highest priority here is to focus on the features that would be used in cloud designs. So IPMI might be much more important than the BIOS setup menu, for example. But at the same time, we don't necessarily disclude the ability to build, a traditional enterprise firmware if you're really interested in doing that. But it's not our focus with Min platforms since that market is already pretty well covered. So can we make LinuxBoot an advanced feature? So let's take a look at performance data from a Xeon E system. This is our full reference implementation with all the advanced features enabled. So as you can see, at least the reference implementation boots pretty quickly. We get through MRC and give or take 200 milliseconds. All of the rest of Silicon init is give or take 150 milliseconds. And really, the big problem is just SPI is slow. So loading code from SPI is slow. And checking code signatures is therefore slow as well. And then the other thing that you'll see here is if you look at the operations being done, PEI and Dixie are actually very well optimized at this point. The piece of EFI firmware that really remains somewhat bloated is BDS, which stands for Boot Device Selection. So this is where all of the EFI drivers generally tend to run because which drivers you run will choose what console you have, for example. If you're using a graphics frame buffer for your console, then you need to run video drivers. If you're only using the serial port, then you don't. But even in a relatively minimal number of drivers being run, BDS is still very large. And if you add a USB keyboard, for example, this 300 millisecond number I have, add 800 milliseconds to that. So we go from 300 milliseconds to 1.1 seconds. So how would LinuxBoot fit into this picture? So Dixie gives us a lot of functionality for the 100 milliseconds that it takes to boot. ACPI is initialized, we get position-independent code, SMM, measured boot, secret storage, secure memory overwrite. There's many features that Dixie gives us for relatively little in terms of boot time, and most of these are pretty important for a product quality Linux system. So I think it makes most sense to keep Dixie and drop BDS. So what does that give us? Min platform plus LinuxBoot really is the ultimate cloud firmware solution. You get the best of both worlds. You can seamlessly switch between LinuxBoot and traditional EFI using one firmware image. So for a cloud type workload, perhaps with containers, LinuxBoot is obviously the best solution, right? You can write your own init scripts in Go, download your own kernel images, download your own container images. It really is a great way to build a cloud optimized system. Now, however, there are several cases where backwards compatibility is really beneficial, even for a cloud vendor. For example, there's a lot of ODM test tools and diagnostic applications written as EFI shell applications. And there's the old mantra of, quote unquote, make boot boring. Uh, EFI really does a great job at just making everything work. It doesn't matter which OS you have, pretty much everything can boot from an EFI implementation. So you get the versatility needed to boot anything you want at any point in time, uh, with a little bit of added boot time, of course. But in your normal case, you can run LinuxBoot and be very fast and very agile. So current status, we currently support a commercially available platform called the Aeon Up Extreme. You can go check that out on GitHub right now if you want to start playing around with Min platform. We're also planning on supporting the third generation of Xeon scalable processors, which are codename Ice Lake and Cooper Lake on Min platform. And we have support for the Wilson City Intel reference board right now. Now, these are pre-release hardware, so the code for it is still under embargo. It will be placed on GitHub once we launch third gen Xeon Scalable. Now, we would love to have one or more OCP accepted boards supported by Min platform as well. If you're interested, please drop me a note. And other than that, our plan is to continue to expand the advanced feature code and quality and increase awareness across the open source community of this new design. So contributions are welcome. Please help us get more boards supported, more chipsets supported. Even non-Intel designs would be great. I have a few links here for all of our repositories. You can find any of our open board packages up on GitHub right now. Add board-specific subdirectories for your favorite board, and get up to stage 4, hopefully relatively quickly and easily. And I believe that is it. If you have questions, feel free to drop me a note, and have a good rest of your day.